welcome again to the course RF transceiver design. We are in module 1 lecture 5 basic of wireless communication. We have discussed in last class about modulation scheme. What are the various modulation scheme, analog and digital modulation. We have also talked about the constellation diagram, QPSK and QAM. All these modulation scheme, we have given the overview. If you would like to go much in the depth, you can refer any communication theory course. So today we are just going to add 2-3 more modules that we have left, and we will cover the rest. So one of the effect that we mostly see in wireless communication is a multipath padding. What exactly multipath padding? That when we are transmitting a signal in air, what is happening that it will not observe a single path because of many obstacles. Let us say here in this example there is a transmitter antenna and receiver antenna. So between these two there is a one obstacle which is a one small building. So there is a one direct path, path 1, and there is another path, path 2. So when there is a signal which will have a different path at receiver, let us say this is a ASK signal, we have already seen in the last class. If this is a amplitude shift keying signal 1010 you have transmitted, one is use a path 1 which is the shortest path. So it arrived early and that path 1 has a reconstruction like this. Now the path 2 will have a delay and this both will be added. So this is this phenomena which will add the delay spread due to the multipath is called a multipath fading. And how can we get rid of this multipath fading? So there is a solution in wireless communication to get rid of multipath fading. So if anyone know, can you think about the which modulation scheme we should use? You can think. I will change the slide. So here the ISI resulting from multipath effect worsen for large delay spread or higher bit rates. So if you have a bit rate which is very high and if your all bits are nearby, then what is happening, this will worsen your detection. And communication, let us say here inside the office and homes, it will suffer from multipath effect. Let us say if your data rate is roughly around 10 Mbps or more than that. So how does wireless communication handle higher data rates? So now there is a solution, as I told, it is a orthogonal frequency division multiplexing, OFDM. So OFDM will help us to mitigate the effect of delay spread, and this we will try to see how the OFDM, what is the basic of OFDM. If you would like to go much in detail, you can go into the wireless communication course. So here in OFDM what happens, there is a some bit stream at XBBT. This is a baseband bit stream and that is denoted by the bit rate RB, and it is applied to modulator at carrier frequency FC. In the last class we have seen it will be up converted to the FC, and it is a very wide bandwidth because the data rate is high. Now in OFDM what we try to do, we will try to divide this FC in multiple subcarriers which is starting from FC1. So in this example FC1 to FCN, and these subcarriers whatever we have identified are orthogonal to each other. So when the multiplication of these two will happen, you will have a less interference with, there is no interference with one channel to other channel because both the channels are orthogonal. So that is why this term orthogonal is coming here, because it is orthogonal, the carriers that are also called the subcarriers. These all are called the subcarriers, and these subcarriers are orthogonal to each other. So, what exactly we are trying to do here? This bit which is a narrow bit, we will try to divide in the n number of subcarrier, and then these bits are spreaded. So, what will happen in last class also we have seen ISI. Here we are trying to increase the effective bandwidth. We are trying to considering reducing the bandwidth here. So, the bandwidth is reducing. So, your time spread is high, and when it will take a different path, you can easily reconstruct the signal. So, this is very wide band and narrow signal, and this is a very short band. There is a small sub channel, and that sub channel is carrying the data which is a widespread data. So, this kind of modulation, and here we are doing a multiplexing because all the carriers are added, that is why it is called a multiplexing, and we are dividing the frequency orthogonally. So, it is a orthogonal frequency division multiplexing. This is a really helpful and widely used multiplexing, OFDM multiplexing, in order to reduce the fading. So, same thing whatever I told is written here. The single carrier modulated spectrum occupies a larger bandwidth. So, in OFDM the baseband data is first demultiplexed by a factor of n and producing a n streams. So, you have a multiple streams and each having a symbol rate. So, before so there is a difference here between a symbol rate and a bit rate. So, the RB is a bit rate and RB by n is a symbol rate because you have a demultiplex and divided by n. So, you are transferring the symbol and that is RB by n. The n streams are then impressed on a n different carrier frequency that I told FC1 to FCN, and it will leading to the multi carrier spectrum. So, sometimes OFDM also is considered as a multi carrier modulation. So, and that because we are considering the FC1 to FCN multi carrier, and here due to low data rate, in each sub carrier there is a low data rate and the modulated signal, that is why can tolerate the delay spread. So, effectively we are trying to reduce the bandwidth, and that will also has a low data rate in each sub carrier. The modulated signal then can tolerate the delay spread. But here one thing to remember that your final total bandwidth will remain same. Only your each sub carrier has a different bandwidth, and that will have a if it is combined into n, then it is a complete bandwidth, it will occupy the complete band. So, this is a widely used modulation scheme and all the sub channels utilize the same modulation scheme. So, let us say if you are using a QAM, quadrature amplitude modulation, then quadrature amplitude modulation in each sub carrier are used, and it is a similar. Let us say if you are using a 16 QAM, so for each channel it is 16 QAM. If you are using 64 QAM, for each channel there is a 64 QAM. So, for example, in IEEE 802.11ag standard, it is employing a 48 sub channels. So, you can see that it has a 48 carrier sub carrier frequencies, and each sub carrier is using a 64 QAM. So, in each for the highest data rate it is a 54 Mbps. So, in each sub carrier there is a 64 QAM and it can able to achieve the highest data rate of 54 Mbps. So, what is the symbol rate? If you want to calculate the symbol rate, we just need to divide 54 Mbps divided by 48, that is a number of sub channels, and again divide by 8 because we have used a 64 QAM. Now, if you use a QPSK or other thing, then this 8 will change. If your number of sub carriers, sub channels are different, then this will change, and the total symbol rate is 141 kilo symbol per second. So, the uh, the symbol rate here it is given, even the time uh, will be increased. So, generally for this kind this this standard it is around 4 microsecond. And one more thing I just want to add here, that there is a guard interval is also added. So, guard interval of few microsecond. So, this guard interval will help to also reduce the ISI, and it is help us to reconstruct the each band, each OFDM carriers more accurately, and you can have a less ISI in complete modulation. So, this is OFDM. So, why we are using OFDM? To overcome the delay spread happening due to the padding. Now, one of the, as we know that we are there is always a trade off. We cannot have everything good. So, what is the trade off that we observed, that OFDM linearity requirement? When we are using a OFDM modulation, we are occupying, we are going to use a multiple subcarriers, and each subcarrier has a many uh, symbol rate. Now, what will happen, because of the different subcarriers, the amplitude varying from the bottom to top has a high variation, and that variation, let us say in this example there is a one output signal, it has a peak amplitude which is very high, and if you see the average amplitude is less. So, this is the difference is too high. So, your power amplifier should be linear, so that it should have the similar pattern which we have made through FDM signal will go over the air. So, this is also called the PAR, peak to average ratio, peak to average. This is also called a PAPR, peak to average power ratio. So, OFDM imposes here a severe linearity requirement on power amplifiers. So, if you are a power amplifier designer, then you need to work hard to get the highest linearity which is possible to overcome this problem of PAPR, peak to average power ratio. It is also mentioned as a peak to average ratio, and it is a quantity measure the signal envelope variation, because there are huge variation over the envelope, and PAR is also defined as a ratio of the largest value of the square of the signal. So, this is a maximum value of the square of the signal, and the average square of the average value of the square of the signal. So, this ratio PAR is important. So, we in reality we do not want PAR should be as high. So, if PAPR, peak to average power ratio, is a high, then the requirement of power amplifier linearity is also crucial, severe. Now, this ratio has a also be defined based on the let us say standards. Whenever standards are discussed, this PAPR is also discussed. So, OFDM has this requirement, and that is a very important to know. So, as we discuss PAR, peak to average ratio, or peak to average power ratio, this is also can be written PAPR, peak to average power ratio. There are three effects which leads very high PAPR. One of the point we have already seen in the last class, that is a pulse shaping. So, this pulse shaping is also increasing the PAR, because there is a, because of pulse shape we are trying to add a variation in amplitude. And there is another point, that is the amplitude modulation scheme such as the QAM. In last class we also seen that QAM has a multi level. So if you are using 64 QAM, then it has a around 8 levels, amplitude will change. So these two things will add too much change in the amplitude or envelope variation. So that is why in orthogonal frequency division multiplexing, when we are using with all these three, it is adding the large PAPR. So there is a standard rule that can be given in the references, that for n subcarriers the PAR of OFDM waveform is around 2 ln of n, and if your n value is a large. So if your obviously if we have a large number of subcarriers, then only we can get the effect of, we can use the orthogonal frequency division multiplexing. There is another problem also is there in when we are using OFDM, that is a spectral regrowth. So this effect also corrupt the adjacent channels. So we will see that how the spectral regrowth happens here. So let us say if you have a ST, which is AC cos omega ct plus phi t. So there is a one signal ST which has a variation which is happening. So it is AC cos omega ct plus phi t. Now here when this signal, there is a amplitude which is a constant, and when you are applying a constant amplitude, there is a frequency domain representation, and when nonlinear power amplifier, it will go through the nonlinear power amplifier. And if we try to analyze the third order nonlinearity by squaring that signal, we will see about third order nonlinearity in the upcoming lectures. So here in order to understand the third order linearity, the cube of the same signal has been done with multiplication of the third order coefficient alpha 3. So when you are cubing this, here amplitude is a constant over the time, and you will have a two quantity, which is a, one is a cos 3 omega ct plus 3 phi t, and another is a cos omega ct plus phi t. So we are interested only in this term, we are not interested in this term, because here the multiplication of 3 omega ct, the variation happening due to the non-linearity is at very high frequency, and that can easily be filtered out. However, if your amplitude is does not have this very continuous envelope, and it is changing with the time, because in OFDM signaling the amplitude is also changing with the time, even in QAM and QPSK also it will change, then we are using the ST, which is SIT cos omega ct minus SQT sin omega ct. So it has a in phase and quadrature both the component, and this SIT, what it means, that its amplitude is varying with the time, and in this SQT also the amplitude is varying with the time. So if you just square that signal, what will happen, that this there is a cos 3 omega ct that roughly will be at higher frequency, but at 3 cos omega ct and 3 sin omega ct, there is a SI cube t by 4, and what will happen, that some of the third order frequency component will try to increase the band, your band level. So it generally if I draw it differently, if it generally looks something like this. So this is nothing but whatever this variation is happening, this is nothing but the spectral regrowth. And because of this spectral regrowth, if your power amplifier linearity is not better, this might be spreaded, very much spreaded. and we need to avoid the spectral regrowth, because as it is written here, adjacent channel, it will corrupt the adjacent channel, because you have a just nearby there is some adjacent channel which is transmitting and receiving. So, this spectral regrowth will corrupt the other channel as well. So, we uh, that is why the requirement of linear power amplifier is high when we are using a complex modulation scheme. So, now we have already seen the effect of fading, what is, how can we overcome the fading, and what are the uh, when we are using OFDM, how, what are the impact on the power amplifier linearity. So, this we already have seen. Now, we will see that how mobile RF communication happens. So, in each mobile receives and transmit information from and to the base station via two RF channels. It is called a forward channel or downlink channel, and the reverse channel or uplink channel. So, there is a downlink will happen and the uplink will happen. So, downlink and uplink channels are there in the mobile RF communication. So, in cellular system, we all know that spectrum is too crowded and it is a costly. So, we need to reuse the spectrum. So, in order to reuse the spectrum, let us say for example, here there is an 900 megahertz, which is a cellular the cellular mobile standard frequency at and it has a bandwidth of 25 megahertz. We need to give this much bandwidth to multiple users, and we need to get a maximum use of this frequency band. So, in mobile communication, the concept of frequency reuse is implemented in cellular structure. So, how exactly it happens? If you have a one frequency f1, then the around the f1 there are, so this is one cell, and there are other, there is a 6 or 5 cells, and that cell has a different frequency. So, this, if this is a f1, that is a f2, f3, f4, f5, f6 and f7, and what will happen then when again you can reuse. So, for this entire cell structure there is only f1 to f6, again the same frequency you can reuse after a say certain cell cover area. So, let us say for example, here f1 and f2 is used, again you can use f1 and f2. So, these methods will help the cellular service provider to use the spectrum efficiently, and it has also some effect due to the, when we are trying to reuse the various frequency. So, one of the problem that generally will come, that is called a handoff. So, there is a base station which is called MTSO, which is defined as MTSO, and there is a one cell A and cell B. So, when let us say you are moving your mobile and your car is moving from one cell to other cell, this MTSO should give the immediately different frequency to other cell, so that there is a, so this is called a handoff, you are handing off one to other. So, sometimes you might have observed the call drop when you are driving or when you are in train, that is happening because of if the proper hands off has not been done, and that is happening because we are using a different frequency. Another problem will come, which is a multipath fading. We already have seen that how can we overcome the multipath fading. One of the way is to use a OFDM signaling. So, generally this loss due to the multipath fading is around 4D, and as shown in the graph it is a 4D in the log scale. So, if you want to overcome the path loss or strong multipath fading, there is a but obvious two method. You increase the transmitter output power. So, that problem can be solved, and another is the receiver dynamic range. So, we will see the dynamic range also much in detail in the upcoming lectures. So, here the transmitter output power, if you try to increase and if you try to have a better dynamic range, then you can get rid of multipath padding. But this when we are talking about increasing the very high output power, on other hand there is a trade off that you have a problem of the linearity. So, you also need to ensure the better linearity and output power, and you need to find out the optimum value of both, and receiver dynamic range is in your hand that can easily be improved by designing a better circuits. So, this is mobile communication that we are deciding. Then there is another issue, that is the diversity, that there are two kinds of diversity: space diversity or antenna diversity. Here employs a two or more antenna. So, when we are using a space diversity or antenna diversity, by a significant fraction of wavelength to achieve a high probability of receiving a non-faded signal. So, if you add a diversity in space or as well as antenna, you can also overcome the problem of the fading. And frequency diversity, that refers to the case where multiple carrier frequency, as we have already seen the OFDM, or the time diversity, which is another technique where the data is transmitted or received more than once to overcome the short term fading. So, instead of sending one at a time, you are sending a multiple time. So, you can also add the diversity. You can add multiple antennas, or you can use a space diversity, frequency diversity or time diversity to improve the fading. So, delay spread, many signals arrived at the receiver with a different delay. This yield to RMS delay spread as large as around several microseconds, and, and hence fading bandwidth of several hundreds of kilohertz. So, thus an entire communication channel may be suppressed during such a fade. So, this can also delay spread can also suppress the entire channel. So, this is a crucial we need to overcome by using the above modulation scheme. Now, we will come to the multiple access techniques. Here in the multiple access techniques there are three widely used techniques. One is a time division duplexing, another is frequency division duplexing. So, the time division duplexing and frequency division duplexing, and for because we want to reuse even the different frequencies here for transmitting as well as reception. So, we will discuss much more in detail about the multiple access techniques in the next class. In this class, we have already seen the importance of OFDM, what are the important terms related to the mobile communication and frequency reuse techniques. So, we will see much more detail about the multiple access techniques in the next class. Thank you.